Hi, everyone. So today we're going to be looking at the fundamental theorem of calculus. So this theorem relates differential calculus, which you already know, with the idea of integral calculus, which we have been getting into. So this fundamental theorem of calculus is split up into two parts. So today we're going to go through part 1, and then later on we're going to go through part 2. Okay, so let's get started with part 1. So if f is continuous, on some interval AB, then the function g defined by g of x is equal to the integral from a to x f of t dt on the interval AB, a less than or equal to x, less than or equal to b, so on the same interval, is continuous on AB, much like f, and differentiable on AB. And here we have the open interval AB. Okay, so f just has to be continuous, but if we define this new function g, then we know that g is continuous and it's also differentiable. Okay, and so this is the more important part, and g prime of x, which we can write as d by dx of the integral from a to x f of t dt is equal to f of x. In other words, taking the derivative out in front, so we're taking the derivative of this, where we have x as our upper bound, we see that the derivative and the integral cancel each other out. So we're just left with f. So here's f of t on the inside, the derivative and the integral, they cancel, and we just left with f, but now evaluated at x. So we evaluated at this upper bound, which was x. Okay, that's it for the fundamental theorem of calculus. Okay, so let's go ahead and prove this now. So proof. Okay, so we begin by defining a small interval in AB. So if x and x plus h are in AB, so if we imagine like the little number line here, if here's A and here's B, then we have x over here, and over here we have x plus h, a little distance apart. Okay, so that's just how you can imagine that. Then, okay, so let's go back to see what we actually need to do. So we need to show that the derivative of g, so g prime, is equal to f of x. So somehow we need to build this into our proof. So remember how we defined derivatives before? We define it as g of x plus h minus g of x divided by h, and then we take the limit. Sorry. Okay, so we're going to do that same idea over here. So let's start off with that numerator. So we have g of x plus h minus g of x. So we're trying to build that limit that we use to define a derivative. So we can substitute g now because we know how that's defined. So this first part will be the integral from a to x plus h f of t dt. So now we have the upper bound being x plus h because the input was x plus h. And then minus the integral from a to x, f of t dt. Okay, so I've just substituted the definitions for g. Okay, so now we can do a little bit of reordering here. So we can write this as the integral from a to x, f of t dt, plus the integral from x to x plus h, f of t dt. Okay, so we can group that together. And then minus the integral from a to x, f of t dt. Okay, so here we're using the properties of the definite integral. So if we have the integral from a to x, and then the integral from x to x plus h, then we can add these two together. So let's just make a little note on the side. If we have the integral from a to c, f of t dt, plus the integral from c to b, f of t dt, then we can combine these two and we get the integral from a to b, f of t dt. Okay, we can combine them because this upper bound matches this lower bound. So instead of doing it in parts, we can just do the full integral from a to b. That's what we're doing over here with this middle term. Okay, so now that we've got that, we can write this as the integral from x to x plus h, f of t dt. Okay, so we've just rewritten this nicely. Okay, so what we need to do now is divide both sides by h, because we want to get the left-hand side to be like the limit definition of the derivative. So let's do that. So here we're going to have g of x plus h minus g of x divided by h. Okay, so that looks like the definition for the derivative, if you want to do it by first principles. And then this will be 1 over h, the integral from x to x plus h, f of t dt. Okay, good. Okay, so that's a good starting point. So now what we want to do is bound this integral over here. So this integral here, we are going to bound it by two different values. Okay, so that's just the idea of what we're going to do next. We're going to bound it by two different values. And then when we take the limit, we will see that the upper value and the lower value approach the same value. So in that case, we can use the squeeze theorem to show that this also approaches the same value. Okay, because it's squeezed between two values that approach the same value in the limit. Okay, so how do we do that? Well, we're going to take this integral and we're going to bound it by its minimum and its maximum. We covered that last time with the definite integral properties. So let's just do a different color here. So MH is less than or equal to the integral from x to x plus h, f of t dt, which is less than or equal to capital M times h. So let's just put on the side what we have here. Little m is the minimum of f on the interval, and capital M is the maximum of f on the interval. And we know from last time that we get this bounds. Okay, so the integral lies somewhere between the minimum area and the maximum area. Okay. So next, the extreme value theorem. So we should have covered this before. So the extreme value theorem says that there exists u and some numbers u and v on this interval x comma x plus h, because remember that is our interval for our integral. So the integral goes from x to x plus h, so that's the interval that we're looking at. Such that, well, remember what the extreme value theorem says. It says that on the interval, there's some number on the interval where f takes its minimum value and some other number where f takes its maximum value. So in this case, we're going to say u gives us the minimum value. So let's just put that in brackets. This is the minimum value. And v, let's say that gives us our maximum value. Okay, and remember that u and v lie on this interval x to x plus h, because that is the interval of our integration here. Okay, so we can replace little m with f of u, and we can replace big M with f of v. So we're going to have f of u times h is less than or equal to the integral from x to x plus h f of t dt, and that's less than or equal to the integral, sorry, not the integral, f of v times h. Okay, good. Now let's divide through by h, so we can get the f functions by themselves. So we're going to have f of u is less than or equal to 1 over h, the integral from x to x plus h, f of t dt, and that's less than or equal to f of v. Okay, good. That gives us a nice inequality. But remember, what is this in the middle here? Okay, 1 over h times the integral from x to x plus h, f of t dt. That looks familiar. That is what we had over here. That's this object over here. And that is equal to g of x plus h minus g of x over h. So we can do a little replacement over there. Okay, so little replacement. So we're going to have f of u is less than or equal to, we're going to replace this with that left-hand side that we saw. So g of x plus h minus g of x over h, and that is less than or equal to f of v. Okay, good. Now remember, way back in the beginning, we said that we wanted this, we wanted to take the limit so that this middle term over here becomes a derivative. So if we take the limit, then it's like we're doing the derivative by first principles. So throughout, we're going to take the limit as h goes to 0. So limit as h goes to 0, f of u is less than or equal to the limit as h goes to 0, and then all of this. And that is less than or equal to the limit as h goes to 0 of f of v. Oh, sorry, it looks more like a u, f of v. Okay, good. Now, before I was stressing the fact that u and v come from this interval over here. So let's just write that out properly at the end here. So u is an element of x comma x plus h. Okay, So what happens when h goes to 0? Well, if h goes to 0, then this interval becomes x, comma, x. In other words, as h goes to 0, you can only take one value in the limit, and that value is going to be x. So as h goes to 0, u goes to x. Okay, because we see that this interval gets smaller and smaller around x, and in the limit, there's only one value that it can take. Same thing with v. So v is an element of x, comma, x plus h. But again, if we take h going to 0, then this interval is going to get smaller and smaller around x until in the limit, the interval is going to have one value being x, and that's the only value that v can take. So v also goes to x. Okay, so that's looking at this term and looking at this term. So if u goes to x and v goes to x, then f of u goes to f of x. And that's less than or equal to. Okay, we took the limit as h goes to 0. Everything in the middle here is just the definition for the derivative. So that's going to be g prime of x. And that is less than or equal to, if we look on the right-hand side, v goes to x, so f of v goes to f of x. Yeah, and we've got ourselves the squeeze theorem now. Or the sandwich theorem. So we've got this inner function, g prime of x, and on the one side, it's bounded by f of x in the limit, and on the other side, it's also bounded by f of x in the limit. So if we take the limit, we see that, so in the limit, this limit over here, that one there, that one there, that one there, in the limit, g prime of x is equal to f of x, which is exactly what we wanted to show. So this is the end of the proof. Okay, so it's not too bad. So let's just go through this one more time. So what we wanted to show is that g prime of x, so the derivative of g, is equal to f of x. So the idea behind this proof is that we try and build up the derivative by first principles. So we look at g of x plus h minus g of x. So remember, that's the numerator for that first principles definition. And then we just substitute in the definition for g. So remember, g of x is equal to the integral from a to x f of t dt. So if I substitute x plus h, then the upper bound now becomes x plus h. If I substitute x, then the upper bound is x. And that's just the definition of g. So now we do a little bit of rearranging here. Okay, so we take this term here, integral from a to x plus h, and we make it go from x. Right, let me use a different color just to show that. So here we're going from a to x, and then from x to x plus h, and then minus the integral from a to x, f of dt. Okay, so why do we do that? Well, we want this over here. Okay. So what we want is the integral to go from x to x plus h. So we need to manipulate this a bit to have this here. But in doing so, we can just get rid of this term and this term. Okay, so let's just make a little note here. This integral, the first one, we split up using this property over here. So we used this property here. Okay, so the integral from a to x plus h, we split that up into the integral from a to x and then the integral from x to x plus h. Much like over here, we have the integral from a to c, then the integral from c to b. So we could have just combined those two. Okay, so then those two cancel, and we left with this integral that we wanted here. Okay, because we wanted these to be the lower and upper bounds respectively. Okay, so that's taken care of the numerator for the definition of the derivative. Now remember that the denominator is h. So we get this formula, which is the first principles definition of the derivative. Okay, so we divide both sides by h, and we get that form of the derivative if we take the limit as h goes to 0. But we do that later on. Okay, now this right-hand side, we can then manipulate some more. Because remember, the idea is to use the squeeze theorem to bound the derivative by two different functions. So we take this right side over here, and we bound it by two different values. We know that any integral is bounded by its upper bound, where you take the maximum of f, and the lower bound, where you take the minimum of f. So that's exactly what we do. We bound it by the maximum and the minimum, and we know by the extreme value theorem that this maximum has some x value associated to it, in this case u. So f of u gives us the minimum, f of v gives us the maximum, and by the extreme value theorem, we know that those two values exist. So we can replace the minimum with f of u, we can replace the maximum with f of v, okay, which we do over here. So now remember that this middle term is almost g prime of x. Okay, we need to divide by h because that's what we had over here in the blue box. So we divide through by h, and now this middle term in the blue box is this right-hand side over here, the right-hand side. So we can replace it with the left-hand side. So that's exactly what we do. Now we want this middle term to be g prime. We want it to be the derivative. So we need to take the limit as h goes to 0. So we take the limit as h goes to 0 on all of the terms. So we know that this middle term will then become the derivative. But what about the lower bound and the upper bound? Well, if we take h goes to 0, then the interval containing u is going to get smaller and smaller around x until only x appears. So you can imagine if we just cross this out, if that goes to 0, then this set from x to x only contains x. So that means u will tend towards x. And by that same logic, if h goes to 0, then v will also tend to x. So we can make a little note here. Both u and v tend to x. So if u goes to x, then f of u goes to f of x. If v goes to x, then f of v goes to f of x. And that's exactly what we do over here. So f of u is replaced with f of x, f of v is replaced with f of x as well, which is why we can now use the squeeze theorem, because in the limit, the upper bound approaches f of x, and the lower bound also approaches f of x. So we have that g prime of x is bounded above by f of x and below by f of x. So by the squeeze theorem, we know that in the limit, it must be equal to f of x, which is what we wanted to show. Okay, so that's the end of the proof. Okay, so let's take a look at some examples or applications of this. Okay, so we've got our first example here. So let's say f of t is equal to the square root of 1 plus t squared. And then we're going to define our g function. So g of x is equal to the integral from 0 to x f of t dt. Okay, that's how we define g. So this is the integral from 0 to x, square root of 1 plus t squared dt. Okay, good. But what is g prime of x? So g prime of x is going to be d by dx of the integral from 0 to x, square root 1 plus t squared dt. Now, note, we're taking the derivative with respect to x, and we've got x in the upper bound here. So we know that by the fundamental theorem of calculus part 1, this integral and this derivative are going to cancel, and we're going to be left with the function evaluated at x. So instead of writing the square root of 1 plus t squared, we write the square root of 1 plus x squared. Okay, we substitute that upper bound over there. And that's it. That's all you have to do. When you're taking the derivative of such an integral, then the derivative and the integral cancel, and you're just left with the function evaluated at the upper bound, provided that the upper bound is just x. Okay, the upper bound can't be x squared or 1 plus x. It must just be x. Okay, now what happens if the upper bound is not just x? What happens if it's some function of x? Okay, that's not too bad. So let's take a look at a case with that. Okay, example number 2. So let's say we want to find d by dx of the integral from 1 to x to the 4. So it's not just x, it's x to the 4 secant of t dt. Okay, so we've got a bit of a problem here because this upper bound is x to the 4, and the fundamental theorem of calculus only works if the upper bound is just x. Okay, but we can fix that. There's no problem there. So instead of writing this in terms of x, we're going to do a little bit of a substitution. So instead of x to the 4, we're going to say let u be x to the 4. Okay, so it's not, so we're going to replace that with u. So how's that going to work? Well, we're going to have to then use the chain rule, because this now becomes d by du, the integral from 1 to u sec of t dt, and then du by dx. Okay, because remember, if you're changing the variables like this, you're going to have to use the chain rule, because something like dg by dx, which is what we want if we define that integral as g, is equal to dg by du, but then remember we also need du by dx. So remember, that's the chain rule. So that's exactly what we're doing over here. We're differentiating by u, which is this first part. So d by du, the integral from 1 to u sec of t dt. But remember, we need to use the chain rule, so we also need du by dx. Okay. So with that out of the way, the integral now is quite easy. Sorry, the derivative is now easy because we have d by du, and the upper bound is just u. So this now becomes sec of u. It's exactly the same as the fundamental theorem of calculus part 1, but instead of working with the x variable, we are now working with the u variable. Okay, but it doesn't matter what we call it. We could call it x, we could call it y, we could call it u. The same thing holds. So this becomes sec of u. Now, what about du by dx? Well, if u is x to the 4, then du by dx is going to be 4x cubed. Okay, so we're almost done. But we can't leave this as u, okay, because remember, we said u was x to the 4. We need to write everything in terms of x. So this now becomes sec of x to the 4 times 4x cubed. Yeah, and that's our final answer. Just make a little note. Everything in terms of x. Okay, so you can't leave it at this halfway stage over here. We need to replace all of the u's with whatever the x function was. Okay, so let's just go through this again. So we're given this problem, d by dx, of the integral from 1 to x to the 4. So that gives us a little red flag there, because the fundamental theorem of calculus only works if the upper bound is x. So instead of writing things in terms of x, we make this little substitution and write it in terms of u. Okay, but if we do that, then the derivative now needs to follow the chain rule. Okay, because this is now a function of u and u is a function of x. So we have to use the chain rule. So if we are differentiating by x, first we need to differentiate by u. So let's put that in blue here. So that's this blue part is differentiating by u. But remember, with the chain rule, we then need to do the second part where we differentiate by x. So that's the second part over here. Okay, so now this blue part becomes very simple. We're differentiating by u, and the upper bound is u. So that cancels because of the fundamental theorem of calculus part 1, and we're just left with the function evaluated at the upper bound. In this case, u. And then du by dx, that's easy to do as well, because u is x to the 4. So du by dx is 4x cubed. Okay, now we can't just leave it as that, because this is our intermediate step. We see we've got u variables, we've got x variables. That's not good. We need everything in terms of x, because that's what we started with. So instead of u, we're going to replace that with x to the 4. And then we can leave 4x cubed alone. That's fine as is. Okay, let's take a look at another example. Oops, sorry. More examples. So this is example number 3. Okay, so for this one, we have h of x is equal to the integral from 1 to 1 over x sine to the 4t dt. Okay, so that's what we're given. And the question is, what is h prime of x? Yeah, we want to find the derivative. So let's write that out. H prime of x will then be d by dx of the integral from 1 to 1 over x sine to the 4t dt. Now, we've got the derivative out in front. We've got the upper bound being 1 over x. Okay, so that's another red flag we've got there. So if it's not just x, then we have a problem. Okay, but that's easily fixed, because instead of writing 1 over x, we can do that little substitution trick to make the upper bound just a single variable, not a function of a variable. So we do the little trick, u is equal to 1 over x. So now d by dx, instead of doing d by dx, it now becomes d by du and then du by dx. Again, chain rule. So d by dx now becomes d by du, the integral from 1 to u, sine to the 4t dt. Okay, but remember the chain rule, we need du by dx as well. So that looks like a y. That's du by dx. Okay, good. Now for this first bit, we're doing d by du. The integral has an upper bound that is just u, so that's perfect. We can use the fundamental theorem of calculus part 1, which says that those derivatives and the integral cancel, and we're just left with the function evaluated at the upper bound. So this becomes sine to the 4u and du by dx. So u is 1 over x. So du by dx is minus 1 over x squared. Okay, but again, we're not done yet. This is just an intermediate step. We've got u over here. Sorry. We've got u over here. We need everything in terms of x. So in place of u, we need to put 1 over x. So this becomes sine to the 4, 1 over x, and then minus 1 over x squared. Okay, and we can leave it like that. Okay, so let's just go through this problem once more. So like last time, we want to find the derivative, but the upper bound is some function of x. So remember, that gave us a little red flag over there. So whenever we have this red flag where the upper bound is a function of x, we need to do this trick over here where we substitute the function for u. So we let u be 1 over x. So now the upper bound just becomes u. And since we're changing variables, d by dx now becomes d by du, and then by the chain rule, du by dx. So the first part, the d by du, that's fine to do now because we use the fundamental theorem of calculus part 1, d by du, and the integral from 1 to u, that's going to cancel out. And we're just left with the function evaluated at the upper bound, in this case, u. And then du by dx, that's also easy to do because u is 1 over x. So the derivative becomes minus 1 over x squared. Now remember, that is just an intermediate step. We can't have u variables and x variables. That doesn't work. So we replace, we replace all of the u variables with 1 over x. And everything is then nice and sorted out. Okay, so just remember, if the upper bound is some function of x, we need to do this u substitution trick over here in blue. Okay, then everything's easy from there. But always remember, if we're doing this change of variables, we need to use the chain rule. Okay, so please don't forget the chain rule when you're doing this. Okay, that's going to be it for today. If you have any questions, again, please just email me whenever you want, or you can WhatsApp me or leave a message on that WhatsApp group. Okay, so next time we will be looking at the fundamental theorem of calculus part 2. So remember, back at the beginning here, this is the fundamental theorem of calculus part 1. Okay, there's the second part that we need to cover. Okay, but we'll do that next time. But in the meantime, if you have any questions, please don't hesitate to email me or WhatsApp me. Okay, I'll see you all next time.